Welcome, Arnab.
Thank you so much for having me. Am I audible?
Yes, you are audible.
Okay.
Here it is Dr. Arnab Purkayastha. He is holding a PhD degree in electrical and computer engineering from the University of North Carolina, Charlotte. He is currently an assistant professor at Western New England University, USA. His research interests include computer architecture, reconfigurable devices for high performance computing on the edge and the cloud, and developing energy efficient solutions to simplify and enhance daily life. Dr. Purkayastha particularly enjoys mentoring students, guiding senior design projects, and encouraging innovation through hands-on learning experiences. I welcome Arnab to deliver his lecture on the topic of accelerators and AI, optimizing energy for a sustainable future. Carry on, Arnab.
Thank you so much for the kind words of introduction, Kaveri ma'am. This has been a really great honor, especially to be an alumni of the institute and also be able to present in front of colleagues, in front of students, and so on. I'll try to first set up my stuff here, and let me present.
Okay, slider showing on. Only see whether the transition is going on.
Yeah, this is good, I think.
Okay, fine.
All right, so welcome everybody. Welcome to this late night talk. I think Saturday 7:30 p.m. It's for me. It's good. It's 9 a.m. in the morning. But you're to all the audience who have been here for a long time. Thank you so much for still sticking around. Thank you to the coordinators for conducting this workshop. This is, I know, like conducting a workshop of this scale is really a big job, big task. So I kudos to all of you. My field is in computing, or computer engineering. So it's interesting when Kaveri ma'am asked me to give a talk on this at this forum. I was like, I'm not an electrical person. I don't know about solar cells or batteries and then I was thinking, like, how do I tie my research to energy? And which actually gave me a really good opportunity to look back at what my background is and how I have been able to traverse through this path, which leads to sustainable energy. So I'll be talking about accelerators and AI. And before I begin, let me also introduce myself once again. This is a little different from what Kaveri ma'am introduced. So this is my journey. I started with a diploma in electronics and communication engineering from TIT. I did a bachelor's in engineering after that. And then I continued with microelectronics and VLSI design. I continued as in doing a Master of Technology from NIT Agartala. And then I switched on, so basically electronics, and then I came into microelectronics and VLSI, and then I switched on to computer engineering. So this was from the University of North Carolina. I started my work in 2017, and I completed somewhere around 22. So this is actually my last day. I was somehow able to get a picture of that. Last week we were having photo shoots all throughout. I don't know if Rajiv sir is here or BQ sir is here. We did photo shoots of with all of you guys during the last week. So some of us are sad leaving the institute. Some of us are happy of going out of the institute. And this is my current role. And this is like my first year students, a picture with my first year students. We have a robotics competition here. This is pretty interesting, hands-on interactive experience. And then this is with a cohort of my colleagues here at Western New England. And this is again another workshop that we conducted. This is a couple of weeks ago. So right now I identify myself primarily as an engineer, researcher, and now a lot of time in educating, mentoring students, and with senior design projects and research outside of this as well, cross-disciplinary, interdisciplinary research. And what I would like to mention is that because of having a diverse background from electrical electronics and then microelectronics and computing, I have had a scope to learn to dip my toes basically in many different waters. So with that said, I also have hobbies. So this is, I like to spend a lot of time in nature. This is in Utah. This is Arches National Park. And then hiking in Vermont. This is, I think, Cadillac Mountain. I don't remember which mountain, but this is in there. And then like to climb trees and also kayaking. I'm really a big fan of kayaking. Apart from that, I also do a lot of reading and blogging and getting, working with high school students as well, working with their projects and trying to build, STEM or science, technology, engineering, medicine with high school students as well. Okay, so that is the introduction. Now let me talk about the flow of this. Of how the flow of this talk is going to be. So I've divided my talk in 3 separate parts: the why, the what, the how. And this is something that I've got from my PhD advisor, who used to tell that, whenever you want to talk about a problem or, give a talk or do anything, you want to first think about why do you actually want to do it. So we'll talk about that. And then once you have a clear understanding of why you want to do this, next you want to talk about what is existing right now. So if you're solving a problem, you see what the problem is, and then see how the problem is being solved now, and then you talk about solutions. So there is the how part that comes in. So this is the philosophy I pretty much follow throughout my life. I will be doing the same thing with this presentation. Now, in my classrooms, I generally have a very interactive environment, high energy students. And most of the time, students do the work. I just kind of guide them, navigate them. So we'll also be having something like this. I try to emulate activities here. So after every single part, you'll have a little bit of an activity. It's not going to be an activity which is like, you're told to work in teams or do a 5-10 minute session. It's just 2-3 minutes simple activities after every session. And I'm doing this for the first time, so I'm not sure if this is going to go well, but I'm hopeful that you'll be liking it. And then at the end, then after the 3rd session, I'll talk about some of the future area of my research, some of the publications that I used for creating this presentation, and we'll stop with Q&A. Now, after every session, you'll have time to work on the activity. So maybe a couple of minutes. And during that time, feel free to ask questions. One of the best ways to learn anything is to just, or know about anything, is just to ask questions. So during the activity space, you can, activity time, you can look at the chat. You can use the chat box. You can post a question, and I'll attempt to answer whatever I can. So this is during the activity, so after every session. If you have any question which was unanswered throughout the session, you can ask me that during the very last, at the very end. So we'll have whatever time we have at the end. I'll stick around and I'll make sure to address all the questions. All right, sounds good. So let's first start with the why. And before we start actually going into the presentation, let me start up with a activity. So this is an intro activity. This is a QR code. I want you guys to spend a couple of minutes, scan the QR code. And this is just asking about you are a presenter, you are a faculty, or about yourself. So this gives me a good idea of who the audience is, and so I can navigate the talk accordingly. I'll also post this in the chat. Okay, so I see some responses coming in. I would highly encourage you guys to take part in this. It'll be really helpful for navigating through the lecture. All right, so as of now, what you can see is we've got some electrical engineering, computer science, network security, um, civil engineering, mechanics. All right, so a bunch of mixed audience, as well as faculties, researcher. Okay, a lot of researchers. Okay, okay. All right, so this is good. So let's now continue from here. All right, so this is the first section. We are talking about the why. Why are we interested in the stock? What is the purpose of the stock? Why are we? We know the purpose of this stock is about sustainable energy. So why are we interested in the stock? The very first thing, and I ask this my students all the time, that you're working in technology. Why do you think energy is important? So the very first thing that comes to our mind is power dissipation. And uh, we'll be going through this. We'll be looking at this from a computing perspective, computer engineer perspective. So we'll talk about how we see this issue of environment and energy, and how does this play a role in our field of work or research. So power dissipation. This is I'll start with some numbers here. CO2e, this is something called as carbon footprint. And carbon footprint is basically a shorthand to describe an estimate of how much you're contributing as pollutant kind of to the environment, but this is in the terms of carbon footprint, not in actual grams. And when I say CO2e, so this is 0.3 grams CO2e. Doesn't mean 0.3 grams, but it's a measure of the power dissipation. So if you talk about a spam email, you get small spam email all the day, right? So you got it contributes to 0.3 grams. A proper email, 4 grams, and an email with a very long and tiresome attachment, 50 grams. Now that's one data. Another data is this. Annually, we see about 62 trillion spam messages that are being sent here and there, which contributes to 33 billion kilowatt hours, and which results to 17 million tons of carbon footprint per year. Now, I'd like you to think, or let this thought sink in for a moment. 17 million tons of CO2 per year. So now the next time when you spend time, writing mindless emails and messages, to your probably someone you like, or to your boyfriend or girlfriend, how are you? What are you doing? Hey, I'm good. I'm fine. Good morning. Good evening. Stop that. You're actually spending a lot of carbon footprint. So power dissipation begins with something as small as that, and then it contributes to a lot more. So whatever communication we are doing here on this scale of with messages and emailing and text, it contributes a lot. That's the first thing that we are dealing with, and this is just one point of problem from power dissipation. Second, temperature. Now, if you have some idea of electrical circuits, electronics, you would know that temperature is really very harmful for your device. Sustained temperatures to your systems, to your computers, to your phones, long-term usage raises the temperature. And this, in general, is not good for performance. Affects performance, which in turn affects reliability, and which in turn affects the longevity of the device. Now, CPUs and GPUs, they oftentimes show temperatures in the range of 70 to 80 degrees Celsius. And this is something that you could do a heat map and see on your own phones or on your own systems. And so since the effects of temperatures are that much, we have to have a lot of cooling mechanisms and cooling systems to take care of this. This is a picture of a data center in a Google data center, which is somewhere in California. And you can see there are elaborate cooling systems for each of these data centers. So that's the second aspect. The third aspect is functionality. So it all started with Moore, right? Gordon Moore. It's all started with saying that every 2 years you have to have more number of transistors packed in one single area or one single chip. More transistors meaning more performance. More performance, that means more functionality. I mean, you compare your phone, which was in early 2000s, to now you have basically a big computer on your hands. So if you see the trends from 1970 onwards to now, Moore's law is still alive, and we are still trying to stick on to this, more number of transistors per device. So functionality is increasing and will keep on increasing. And we have to know that, we have to be aware of that. Every single day there is a new video coming up, we keep on TikToks or YouTube videos. Every single day new content comes up in the market, and so more functionality needs to be available on your every single day. Finally, all of these things together combine and tend to the main thing, that is cost. So it's all about the money, right? How much money are we able to spend on all these different things? So when you want to say you want to have cooling stations for your data centers, how much money you want to spend? You want to increase functionality, how much money you want to spend? So these four things have been the driving factor of computing industry in general. And from my VLSI background, as a VLSI engineer, what I really think is when you want to make a design, you think about power dissipation, temperature, functionality. These three are the top three criteria that you want to first deal with. So this concludes the first part of the talk, which is why this talk. That is, why is energy important? Why are we actually asking this question? So now we'll have our second activity. This activity is prior knowledge. We just want to look at what knowledge you have about the topics that I'm going to continue from here. So we'll take a 2 minutes time for this survey. Once again, just scan this QR code, and let me also put this on the chat. And I'd like to remind, like, if you have any questions for each of these sections, this is the time you can just push your questions on the chat and I'll be ready to answer. All right, so we've got some responses. Just give a couple more minutes and continue. Perfect. Now let's move ahead. All right, so the first part of the story was over. That's the why. So I'll just do a quick recap of the why. Why are we concerned about energy at all? Uh, Power dissipation, that's the first thing. You want to consume the least amount of power as possible. Secondly, the functionality. Think about more Gordon Moore and Moore's law, and you want to do keep on increasing the number of applications. You want to keep on increase the number of available data on the data, and you want to keep on increasing the number of transistors. So more functionality, more performance. Temperature, we want to reduce the temperature. If you keep on using a device for sustained longer and longer period of time, you're affecting the reliability and eventually the longevity of the device. And to cap it all off, cost, right? Everything is about paisa. So now let's look at the second part. So this is the problem. How do I solve the problem? Or what are the existing things that or existing technologies that help solve this problem or help solve power dissipation, temperature, and so on and so forth. So the what? So this is our role as engineers. We engineers have to strike a balance between all of these. So the way I see it, it's a game of trade-off. Right? You have to increase performance. You have to optimize applications. At the same time, watch out for the environment. And this is not something that we just as computer engineers work, but it's like all engineers across cross-disciplinary platforms are somewhere or somehow involved in this chain. So we have to play this game of trade-off between different parameters. So what is out there for us in the market right now? There are three technologies that are right now available in the market in terms of computing: CPUs, GPUs, and FPGAs. So I saw many of us are familiar with CPUs, GPUs, so that would be really awesome. So CPUs, GPUs, and there are some other devices or types of devices also, but primarily the main three distinct criteria of this: CPU, GPU, and FPGAs. We'll look at each of this, and we'll look at how each of these perform, and we'll look at how each of these are dealing with our problems that we just discussed, the why part. And so to start with understanding this, I want to take a very simple example, which is of an image of a video frame. And I continue with how this then ties up with CPUs, GPUs. So consider a video frame. So this is a video frame which is showing the Earth's movement, the satellite recordings of Earth's movement over for a period of time throughout the day. If you think of a video frame, it's nothing but a set of frames, individual static frames, which collated together becomes a video frame. And each of these individual frames are comprised of nothing but pixels. A pixel is a piece of information that starts at the very top and then at the very end. So if I talk about this particular frame is a 512 by 512, that means 512 pixels by 512 pixels, 512 rows by 512 columns. Each of these can be numbered like A1, B1, C1, A2, B2, C2. So what we are trying to understand here is to get, say, if your first frame is an A frame, to get to frame C, you have to do some computation here, and I'm doing a very simple computation, which is A times B, which gives me C. So so this is how I get a video frame. Now let's look at how this happens from the CPU perspective. So CPU, or general purpose computers, or in computers in general, these came around 60s, 1970s, and became the first professional computer or marketed computer. Intel 4-bit 4004 was something around 1971 or 72. And gradually this CPUs have been the dominant player in the market. And what CPUs are inherently sequential machines. These are something called as ISA specific, ISA meaning instruction set architecture specific. So that means there is, if you have some familiarity with computers, the ISA, which will be ISA, is nothing but your, how your address bus is designed, how your data bus is designed, where is the program counter, how big is the program counter, how much is the secret stack pointer, and then the memory and those kinds of things. So all that is your ISA. Now this is limited. Of course, you are limited to the number of things you can only put so much in one chip, right? The number of transistors, the number of the very first CPUs that came in the market were the very first idea of CPUs, that is CISC-based systems, which are all very sequential in nature, and so therefore not efficient. Now, I'm not diving into the deep architectural differences, but I just want to point out how this operation of getting one frame for the other would happen from a CPU perspective. So what I'm doing here is A11, row pixel number 1, that is row 1, column 1, times pixel number 1 of frame B, that is row 1, column 1. It gives me C, row 1, column 1. So A11 times B11 gives me C11. Now this in a CPU happens like this. So first computation, this is A11, B11 gives me C11. A12, that means first row, second column. B12, first row, second column of B. It gives me the first row, second column of B. So this goes on one after another. So essentially travels like this, and you get A row 1, pixel number 512, that is column 512. B1 512 gives me C1 512. Once this happens, the CPU then moves to the next line. And then I again do the same computation, this time with row 2, A21, B21, A22, B22, and then A2 512, B2 512. I keep on doing this one after another, or one after another. And so it's inherently sequential operation. It is not efficient. It's very, very slow. However, it is good for sequential tasks. Now I put a small asterisk here because the CPU that I'm really discussing or comparing this is the older generation of CPUs, which were purely CISC-based systems. If you think about newer generation of CPUs, we have more parallelism and multi-threading, multitasking, those kinds of things. But this is just for a CPU. If you look at CPU as a single sequential machine. Now, how would this have happened in a GPU? Now, GPUs became popular somewhere around 1980s. Actually, came in 1980s and became popular later on, very, very late popular. The overall idea of GPUs was a SIMD-based machine, that is single instruction, multiple data. That is, you are going to work with a lot of data. Given infinite resources, you can work with a large amount of data at the same possible time. And so GPUs had this idea of what we call as MAC units. If you take a NVIDIA advertisement, just look at it and it just tells you 15,000 or 20,000 MAC units, or they say cores. So basically MAC units which do what? Which just do a simple multiply and accumulate operation. So the idea of GPUs came from the fact that we are looking at, if we have more data, how we perform more data. And this data, if there is no dependency of one data over the other. So as an example, in this case, if I have to calculate C11, I have to just work upon A11 and B11. And if I have to calculate, say, another pixel like C512, I just need my pixel A512 and B512. If I have to calculate something like C256, they have to just work with pixel A256 and B256. So in situations where there is no dependencies, this is a very, very great architecture, because CPUs are horrible in these situations, right? Very sequential and will take a lot of time. This is very good because you are able to work on multiple things at once. This is good for parallel tasks. And so there was this entire shift, especially in gaming industry and medical appliances, medical imaging, vision algorithms, where you have to do a lot of parallel tasks at the same time. And so whenever there is any kind of parallelism involved, GPUs would be able to rule, the best to rule. Now, these are also not very efficient. These are also ISA dependent. They also they have an instruction set. However, they did gain a lot more traction than CPUs, and were good at jobs which the CPU was not. Now, on the flip side, if I say there is an operation which say if I say my pixel number C12 will depend on the result of my previous pixel, say C11. If that is the case, that is, I have to depend on something else. It's a very sequential operation. In that scenario, GPUs will not work good at all. In that scenario, of course, you would prefer a CPU over a GPU. So this is what happened in the industry. For parallel processing tasks, everything shipped to GPUs. For sequential tasks, shipped to CPUs. So this was the second type of architecture. This is the second type of architecture in the market. That's GPUs. The third one are FPGAs, called as FPGAs. These are another type of devices, another class of devices. These are called as field programmable gate arrays. They do not have an ISA. So basically, an FPGA is some configurable logic blocks, which can change depend on the application. So they are very, very, very application specific. So something like the multiplication that we did, which is a very parallel task, this can suit an FPGA. And also, whenever you have a new application which is very sequential, that also can suit an FPGA very well. So since you are able to reconfigure the logic, runtime reconfigurable logic, FPGAs are really I would say, sweet spot between CPUs and GPUs. And finally, another class of devices that is ASICs. ASICs are application-specific ICs, and ASICs are nothing but your individual chips. Say, for example, your washing machine, your embedded devices, IoT devices, refrigerators, calculators, things which are doing only one specialized task. They are not reconfigurable. They are efficient because you are going to tailor your device to that particular task. So in general, there are these four kinds of types of devices. And now let's see where they compare. Now, if you look at the spectrum here, on the y-axis, I've got flexibility, or I would say reconfigurability. How much can you change? And on the x-axis, I've got performance or power efficiency. Or power efficiency, performance per watt, or efficiency, power efficiency. On the very top end of the spectrum, you have GPUs and CPUs. CPUs more flexible than GPUs, but in terms of power, very, very poor, very, very less efficient. Consumes more powers, underutilization of resources, and so on and so forth. Very much reconfigurable, but not efficient. On the other end of the spectrum, you have application-specific ICs, ASICs, which are very much power efficient because you're making the device for a particular application only. So very application-specific, very efficient, but not flexible. You cannot use the same ASIC for doing some other task. In between, the reconfigurable logics, or the FPGAs, are what has like best of both worlds. Flexible, not so much; efficient, not so much, but somewhere in between. So the whole, if you look at the whole talk about the Y part of this lecture, when we looked at the different components that affect the energy. So that ultimately tells you that reconfigurable logics have a better chance at becoming a more dominant device in this scenario where you are thinking about trade-offs. Now, how does this tie to AI, or artificial intelligence? AI, if I were to classify the current AI market, or in an AI scenario right now, We have four different types or kinds. Machine learning, which is just looking at some data, doing some pattern recognition, designing some algorithms for pattern recognition. Neural nets, which is trying to mimic the human brain, looking at some features, parameters, trying to mimic the brain. Natural language processing or large level language models, that is something like ChatGPT or Copilot and so on and so forth. These also have been are also something which have been driving the AI trend now. And then the robotics. Robotics, of course, how can you use machines to assist? Uh, if you think about all these, there is uh, one uh, point or one important thing that you can look at is data. You're looking at data. We're looking at tons and tons of data. Just look at neural nets, for example. Neural nets actually came a long time back in 1960s, and then some research in 70s. They had existed then. But due to lack of compute power, due to lack of resources, due to lack of specialized hardware, neural networks didn't really take any traction. If you look at a simple neural network, what do you see? On one side, you have the inputs which are nothing but features or parameters of a particular object or whatever you want to recognize as. And then you have a set of hidden layers, which are doing some mathematical operation, trying to predict a particular outcome as you would want to. And then there is the output part, which is basically prediction. And so this was the general idea of a basic convolutional neural networks. And so you have a simple image, and then you can predict that image. However, because of the unavailability of specialized hardware, we were still lagging behind a lot in neural nets. And today, with more advanced architectures, GPUs, and FPGAs, and different accelerators in the market, you see AI has got a lot of traction now. So if I now look at any artificial intelligence network or any problem that deals with artificial intelligence, I can list in these few points. That is, I mean, these are the main few points of basic AI network: quality and quantity of data, a lot and lots of data. The more data you have, the more it is valuable for your network to be trained. And so you need a lot of data to understand, to do better prediction, to become better at prediction. Of course, the quality of data, but also the quantity of data. Today, with deeper networks, network architecture has been changing with deep neural networks, deep learning DNNs. You keep on adding more network layer, and you see better prediction models coming out of that. Now, applications of AI, they can be massively parallel, something like matrix multiplication, or something like the image example that we just saw. It can be massively parallel like this, or it can be inherently sequential. It can be one after another as well. And now, if you compare, if you talk about AI training, and this is like the most important or the most power-hungry section of an AI architecture, you would see that you're looking at a lot of data. You're trying to somehow work with it, save it, work with it to give better results. And so most of AI training nowadays happens in the cloud versus edge devices do more of the inference part of it. And so all these all these things tell you that the very first part of the section, the why part of the section, why is it so much relevant? So we looked at the what. we looked at the why. Now we looked at what is available in the market, what is available in terms of technology, and how these things can help us. And now we need to see at how we solve the problem. What are the existing things that can solve the problem. So with that, I'll stop with my second part of the topic, and I'll give you a simple activity once again. This is a recap of the what section. So once again, let me just copy paste this, and feel free to ask questions at this time. This is a very good opportunity to have your doubts cleared. So this is the third one, and let me share my screen once again. All right. Let's, so we've got enough responses. Let's move on to the next section now. And before that, I actually have a question on the chat. How to reduce the energy consumption of sensor nodes while providing security to that system? Energy consumption of sensor nodes while providing security. So you're talking about two different things, sensor nodes and security. Uh, Again, this is another, I'm not sure if I understood the question properly, but uh, if you think about energy and security, these are two different things. I mean, although there is a lot of overlap in terms of matching the trade-offs, but to my mind, I think security is a different aspect. Uh, of course, if you are looking at nodes, if you are able to find out the power consumption of each of these nodes, you would be able to you'd be able to tell, like, more secure operation would mean more more data say you're talking about more data compression, more encryption, stronger encryption algorithms. Where do you run those algorithms? So you want to think about that, and so then there would be some more of how do you incorporate accelerators, or what application, what accelerator runs your particular application. So then there would be the, the point of trade-off between the application that you're running and your security based application, and uh, saying how do you reduce the energy consumption. But if I didn't understand your question well, please feel free to let me know um, more. But this is what I understand, that if you think about accelerators and you think about applications that you want to run, uh, you look at the application nature, the type of the application, and then you run the application based, and you choose the accelerator based on that application. So we'll actually look at some of the things that I've done in my research, which would give you more pointers to the question that you're asking. Uh, and I see Prashanto Sarkar. He used to be my classmate. Hi, Prashant. All right, so let's move on to the next thing. That is the last part of this talk, the how part. All right, so we looked at the problem statement. We looked at what are resources, what are the current things that are going on in the market, and we talk about how do you solve those problems. How do you make energy consumption better in devices which consume the least energy efficient devices. And so the way we approach this problem is from two ends, hardware and software. Let's look at some of the hardware solutions. Now, when I say hardware, it starts with semiconductor modeling devices, VLSI, and so how are you going to make energy efficient processors? In the recent years, there has been a lot of work in how do you make low power CPUs, specialized processors like TPUs or TensorFlow processors. You must be familiar with Google TPUs. So these are very, very efficient processors which are tailored to run some applications. So a Google TPU is very popular for DNN-based architectures. So this is one solution. You come up with energy efficient processors which are able to solve which are able to work with the applications consuming the least amount of energy. Then something called as dynamic voltage and frequency scaling. This is again from the VLSI part. How do you have the limitations of your voltage and the clock speed? How are you going to play with that? How are you going to play with that and make an energy efficient design? Of course, using accelerators, FPGAs or GPUs, better, of course, better devices, better FPGAs or GPUs. Efficient cooling systems, one of those that is, how are you able to make more advanced cooling systems than what is existing? It used to be pure water-based systems, and now there are nitrogen-based. There are many, many different types of designs, and so hardware solutions is one of them. Now, advantages and disadvantages of both. Again, tailored solutions, tailored designs. So if works something for, say, CNN or DNN based applications, this will be really, really useful. It will be really, really helpful. On the other hand, making a new architecture, making a new device, or making even little incremental improvements on our actual hardware or actual architecture requires a longer development time. So from concept to ideation, it will be it'll take a long time, and you would not be able to meet with the demands of the market during that time. And the other thing is high upfront cost, the cost of research and development of such a new project, new hardware would be really costly. So this is some of the things about hardware solutions. Software solutions, designing efficient algorithms. Uh, from late 90s to now, what we have been seeing is how are you able to uh, make efficient algorithms? How are you able to distribute workloads properly? How are you able to make things like multi-threading, multi-processing, those kinds of things, energy aware, scheduling algorithms. So those things have been the push at this for software. The other thing is, when you look at an application, you try to identify the parts of the application which can be run parallelly versus parts of the applications which can be run sequentially. So you divide that, you give the workload that can be run parallelly to a GPU or an accelerator, and then the work that can be done sequentially to a CPU. So that solves your problem. So these are some of the things that have been around for software solutions. Now, again, advantages and disadvantages of this. Cost effective, easier to implement, of course. You need some IT people and computer science, computer engineers who are working all the time for developing software solutions. On the flip side, requires domain knowledge, requires expert knowledge. So how do you balancing, playing with the trade-offs, that is totally a different, it's an area that requires expertise. So yes, some of the advantages and disadvantages of software solutions. The third one is hardware software co-design, and this is basically my work, and I'll spend a few minutes now to talk about how I have been using this, or how my research has been involving hardware software co-design, and how that has been how we have been able to make sustainable solutions or energy efficient solutions from proper hardware software co-design. Now, if you think about hardware software design, this is what my PhD work was about. So I was really interested in FPGAs. Accelerators was my passion. Accelerators, GPUs, of course, and also FPGAs, mainly FPGAs. And so when I started my PhD work, I started with FPGAs. And my problem statement was, how do you make efficient solutions based using FPGAs? Now, at that time, and especially in early FPGA architectures, when FPGA came out, the programming platform or the programming paradigm that FPGAs were using was HDLs, or hardware description languages. So we had Verilog and VHDL. Now, although easy to understand, PHDL and Verilog, and work with, uh, it becomes tough, or it becomes really complicated to use when you are scaling up solutions. It started because FPGA started with as a DoD project or defense project, and this started with defense. Never really went on to the industry because of programming challenges, and instead came to the academy. So FPGAs, although were power efficient, reconfigurable, better than CPUs and GPUs in some senses, but due to the programming difficulties, you would not be able to extract the best out of them. Now, luckily, this was in 2014, and I started my work in 2017. 2014, there was a programming language called as OpenCL. That language started to give support for FPGAs. So by the time I started my work, the OpenCL had matured, not matured, but at least it was in its in initial stages. It was giving support. There were a lot of bugs and known issues that we had to fix. But even then, there was the scope that you can scale up. It was based on C++, and so you could scale up your design now, which was limited to using HDLs, now becoming more to a more powerful programming platform. So what I tried to do was I tried to combine the best of each. So I tried to work on FPGAs. I tried to get the best of FPGAs, and I tried to improve the programmability of OpenCL. Now notice OpenCL was initially developed for CPUs and then for GPUs. It was never really mapped on for FPGAs. So much of my research has been to map OpenCL to FPGAs and extract the maximum parallelism potential for that. And so solutions that I did was, making efficient architectures, giving different tools, many optimizations and automation tools. That was the main contributions to me. So now I'd like to talk about the three major contributions. OpenCL parallelism taxonomy, LLVM-based decoupling, and throughput-oriented design for cloud FPGAs. The first one was making some optimizations, algorithmic changes to individual applications. I tried to mimic an FPGA to work like a GPU. So, GPUs have this, structure of inherently parallel, massively parallel device, parallel structure, and you can do many operations at once. I tried to do that. I tried to emulate the same thing on an FPGA. So the whole goal of this project was to make FPGAs as powerful and as parallel like a GPU. So we did this over a bunch of real-time industrial applications, Rodinia benchmark applications, and we found out some of the key results were like, so for some applications, FPGAs perform very, very, very much better than GPUs. For some applications, it didn't because of some inherent properties of the applications. But in general, the performance was way, way better. When we compared performance, we compared bandwidth. We also compared performance per watt, which is nothing but energy efficiency. And this is me just showing off the number of experiments that we did, and got some papers published based on the first work. The second work, LLVM-based memory decoupling. This was a more challenging work. This was entirely new work. We used something called as OpenCL pipes, which is again a programming construct, and we developed an intelligent tool. Now, the thing that we were trying to solve here was the issue of, we noticed that FPGAs, like any other devices, have a cap on memory bandwidth. So, the issue of memory wall. And we tried to solve this memory wall. So that was one problem. The other problem was uh, due to memory wall, there was also a problem of memory stalls, which occur not so much because of bandwidth, but rather because of the way in which the scheduling is done inside an FPGA when it is mapped to OpenCL. So we try to come up with a tool, the input to the tool would be an application. Say, for example, I'm talking about this application, hotspot application, which is a physics-based application, and I give this tool to give this application to my tool. What my tool does, it parses through the application, and it finds out variables which are dependent on any other variable, and variables which are not dependent on any other variable. So do different types of variables. We call these variables as decouplable and non-decouplable. And so what we did was, using the OpenCL pipe construct, which is a very efficient way of working with decouplable variables, we were able to break our applications and at the same time think about the consistencies, data consistencies. So we were able to break the application, and for all the decouplable variables, we are able to make those variables work faster, or those computations run faster, versus variables which are not decouplable was working in the same regular fashion on FPGA. So this was a pretty challenging work. We submitted this into multiple journals. We finally got it in a good one. And so you can see what this shows as, this figure shows. Again, we are doing a performance per watt comparison, which is energy efficiency. And we are looking at baseline versus something called a subkernel. Subkernel is the one that we designed. So we looked at baseline performance of some applications, and we tried to do two types of optimizations. One is using local memory, which is a pretty common optimization that is done in GPUs. We did that for FPGAs, and also subkernel optimization, which is using OpenCL pipes. And based on that, we again got some promising results for some applications, not for all of them, but still we got some promising results using decoupling. This was the second one. Now, comparing the insights of the first two works, we went ahead with a plethora of works, many works which mainly focused on using the applications that we worked with on and applying them on the cloud, or running them on the cloud. So we went from the edge to the cloud. And this time we tried to also solve other problems in OpenCL and FPGAs, like design time. One of the major challenges of FPGAs is the time that it requires to, we are saying reconfigurable, but it takes time to run such an application. So how much we try to make design time faster. Of course, performance, bandwidth, and energy efficiency, these were also some of the main things that we try to solve. So this is in total of what my research is. Again, I would say, if you are interested more about these particular any of these areas, please reach me out. We can discuss about this. And I'm still working on some of these topics. There are many trajectories that this research can take. So happy to continue the discussion further. So this is all about my work, and let's move on to the future. All right. So the future here, uh, the scope and opportunities uh, in all these kinds of computing and devices, and future for computer architecture, for if you're saying for the next 20 years, what I firmly believe in is that there will be a lots and lots and lots of computing. We are still going to work with a lot of data, and we are still going to be bounded by resources. We are still going to be bounded by utilization. So a lot more compute, and I don't see quantum computing really coming in the next, 2 or 3 decades. So there is a lot of scope for us. The future is accelerators. Initially, the designs, initially systems would run like this: that you have a CPU which is doing the whole job, or an FPGA which is doing the whole job. But now with newer processors, uh, you have one chip with a CPU, with a GPU, with an FPGA, and they keep on adding new and new and new and newer devices. I remember in 2018 when I heard of Intel Xeon processors, they had come up with a CPU and a GPU based design. And now, I mean, on my phone, I have a GPU and CPU running. And so the whole idea is how do you see the future of accelerators being that, for the next few decades, we still have a lot of scope in both jobs and research in accelerators. The other opportunity is energy aware algorithms. So computer science engineers, computer technology engineers, you have a lot of scope. We spoke about briefly about workload balancing and scheduling. So there is still a lot of scope in algorithms. So one example that I showed you of pipes is just one flavor of this. So we can have a lot more opportunities from energy aware algorithms. So computer engineers, a lot of scope as well. Job opportunities, and this is something that I would highly recommend, highly ask the faculties who are in this talk to think about this, that there is a lot of scope. If someone comes and asks, if a student comes and asks you, do I have a future learning about FPGAs or GPUs? Yes. The answer is a resounding yes. Please encourage your students to join this field. There are a lot of jobs both in hardware and software. Of course, jobs like testing are now gone, right? With AI, you have with more automation, you have base level jobs. Some of the very basic level jobs are gone, but there is still a lot of scope in both hardware and software in this field. So that's the list of opportunities. These are some of the publications that I used for this talk. These were some of the ones that we used, that I published during my time in UNC Charlotte. And if you need any of these, or if you need any data which in relation to each of these projects, I would be more than happy to talk. This is a really exciting time for computer architecture accelerators. We are looking at a lot more towards making sustainable solutions. So if you are interested, please reach me up. This is and if you're interested about any of these papers, or journals or papers, just reach me out. Finally, I have one last thing from you before we go to the question answer session. One last feedback. I'll again copy paste this on the chat. And please provide your honest feedback of how this session went. And if you have any suggestions, please let me know. All right. So while you take your feedback, I would like to open the floor for any other questions and answers at this time. Uh, and I'm sharing the my email. You can reach out to me on email. I'm not so much active on social media, but you can of course reach out to me on LinkedIn, and we can connect from there. I'll be happy to share ideas. If you have any ideas for partnerships or collaborations with your students, we can work as a team. International partnerships really work out good. If you have any if you have any project ideas that you want to explore, please reach out as well. If you are applying to any university here as a student in US and you need any help, working with your dossier or your package, and just reach out as well. I'm free to. I'm here to help. Yes, so I see Jibon sir is this. So this is yes. I If you look at my slide, it's my email ID is shared. You can reach out to me in both whichever you want. And yeah, I'll also paste this to the link. Actually, if you need if you need more about contact information, you can reach out to Kaveri ma'am. She has all my details. She can help you with that as well. All right. If there are no other questions, then I would like to end my talk here. Again, thanks. Thank you so much to the coordinators for having me. It was really exciting to present at my home institution. And I would really be happy to look out for opportunities in the future.
Dear participants, can you can ask any question. Expert is waiting for your question. You can ask any question.
Hello, sir.
Yes.
I really enjoyed your presentation. It was well organized, clear, and engaging. And
Thank you.
as a computer science student, I have one query, but it is regarding wireless sensor network. I some time ago in the chat box I sent one question, right? So I couldn't explain the question. So I want to explain it. Actually, I was talking about wireless sensor network. So we have seen generally when we like want to connect security measures to wireless sensors or the sensor in the sensor networks, uh, or in the sensor devices, we generally see the energy dissipation is more. So, is there any energy aware algorithm or anything? So, is it possible to use that algorithm to just minimize the energy consumption?
Yeah. So again, thank you so much for that question. Uh, so from an algorithm perspective, if you look at the application, so I would like to ask what kind of security applications or algorithms you're running.
Generally, like I'm talking about um, um, energy dissipate to reduce that energy consumption attacks only, like the DOS attacks, or what to say, the cyber physical attacks. I'm talking about the cyber physical attacks. So we so um,
So yeah, so
to
if you look at the DDoS attacks, right? So if you look at DDoS attacks, you'll find again some. Now I won't be able to give you actual pointers to a particular application, but there would be two areas once again to work with. The software part, that is trying to optimize algorithms based on things like load balancing is one of the common things that you do, right? When you make a security application, how is it, what kind of encryption are you doing, and how are you able to better manage the workload that you're dealing with. So that could be one of the things from the software perspective. From the hardware perspective, things like newer architectures, like LoRa networks, which are more efficient sensor-based networks, that also can be utilized, but depends on the case case by case basis. That could be some of the solutions.
okay, okay, fine. Thank you.
Okay, any other participants? Okay, I think no one have any question. Thank you, Arnab. What an interactive session it was. I had enjoyed a lot. I think not only me, every participants have enjoyed a lot. You have discussed about energy loss, how they are occurring, how to reduce the energy loss, effect of AI, ANN, accelerators on the system to reduce the energy loss. You have also discussed about the power efficient FPGA, OpenCL, etc. Overall, your class is really very interesting. Okay, thank you, Arnab.
Thank you so much once again for having me, and I'm glad you liked the talk. And there is like, once again, I would like to emphasize, there is a lot of scope, and if any of the faculty members you want to reach out for any other collaborations, please feel free to reach out. Thank you so much.
Thank you all participants for the patient hearing. Tomorrow our class will be started from 6 p.m. You please join, and the attendance link is given in the WhatsApp as well as in the chat box also. You can give your attendance. Okay, thank you all. Good night. Tomorrow we shall meet. Tomorrow, that is not tomorrow, on Monday we shall meet. Tomorrow, Sunday will be closed. Okay, thank you all. Thank you, Arnab.